The impact of losing a current transformer on revenue measurement isn't straightforward. It depends on several factors, including the specific metering configuration and the type of load connected to the transformer. In a typical 36,000 volts delta transformer with a three-phase meter, the loss of a single current transformer on phase C will indeed result in approximately a one-third reduction in the measured power. This is because the total power is calculated as the sum of the power measured on each phase. However, the impact on energy measurement is not always proportional to the power reduction. If the load is balanced, the energy measured by the remaining two current transformers will be accurate, and the loss of data from the third current transformer will have minimal to no impact on the overall energy measurement. If the load is unbalanced, the loss of a current transformer will introduce an error in the energy measurement. The error depends on the specific load pattern and the metering configuration. There are several factors to consider. Firstly, the type of metering configuration, for example, single versus three-phase metering, or the use of summation current transformers, can affect the impact of current transformer loss. Secondly, the characteristics of the load connected to the transformer, such as balanced versus unbalanced or inductive versus capacitive, can also influence the impact. Thirdly, comparing average revenues during similar periods can provide some context, but it may not accurately capture the impact of current transformer loss if the load patterns or metering configuration have changed. To determine the most accurate way to recover revenue, you should firstly consult with the utility provider who is requesting revenue recovery to understand their specific metering configuration and methodology. Secondly, review historical revenue data and load profiles to identify any anomalies or trends related to current transformer loss. Thirdly, conduct a load study to determine the nature of the load connected to the transformer and assess the potential impact of current transformer loss. If necessary, consult with an independent expert or engineering firm to provide an unbiased assessment of the impact of current transformer loss. Based on the findings, you can negotiate a settlement with the utility that is as close to actual usage as possible. Now let's delve a little deeper into each of these aspects. When we talk about metering configurations, we need to consider how the current and voltage are measured to calculate power and energy. In a three-phase system, there are several ways to connect the meters. One common method involves using three current transformers, one on each phase, and three potential transformers, also one on each phase. These transformers step down the high voltage and current to levels that the meter can handle safely. The meter then calculates the power on each phase and sums them up to get the total power. Another method uses only two current transformers in what is known as a 2.5 element metering system. This method relies on mathematical relationships between the phases to infer the current in the third phase. If one of the current transformers fails in a three-current transformer system, the meter loses the current information from that phase, leading to the one-third reduction in power measurement that we discussed earlier. However, in a 2.5 element system, the impact can be more complex depending on which current transformer fails and how the meter is programmed to handle the missing data. The balance of the load is crucial in determining the accuracy of energy measurement after a current transformer loss. A balanced load means that each phase is carrying approximately the same amount of current and has the same power factor. In this scenario, if one current transformer is lost, the remaining two current transformers can provide a reasonably accurate estimate of the total power, assuming the balance is maintained. However, real-world loads are rarely perfectly balanced. Unbalanced loads occur when different phases draw different amounts of current. This can happen due to various reasons, such as unequal distribution of single-phase loads or the presence of three-phase motors that are not loaded evenly. In an unbalanced scenario, the loss of a current transformer can lead to significant errors in energy measurement because the remaining current transformers do not accurately represent the current in the missing phase. The type of load also affects the power factor, which is the ratio of real power, measured in kilowatts, to apparent power, measured in kilovolt amps. Inductive loads, such as motors and transformers, cause the current to lag behind the voltage, resulting in a lagging power factor. Capacitive loads, such as capacitors, cause the current to lead the voltage, resulting in a leading power factor. A low power factor increases the current required to deliver the same amount of real power, which can lead to higher energy losses in the system. When a current transformer is lost, the accuracy of power factor measurement is also compromised, especially if the load is unbalanced or has a significant reactive component. Historical data analysis is a critical step in assessing the impact of current transformer loss. By examining revenue data from previous periods, you can identify trends and anomalies that may be related to the loss. For example, if you see a sudden drop in energy consumption after the current transformer failure, this could indicate that the meter is underreporting energy usage. However, it is important to consider other factors that may have affected energy consumption during the same period, such as changes in production levels, seasonal variations, or the implementation of energy efficiency measures. Load profiles, which are graphs showing how energy consumption varies over time, can also provide valuable insights. By comparing load profiles before and after the current transformer failure, you can see how the load patterns have changed. This can help you determine whether the load is balanced or imbalanced and whether there are any unusual fluctuations in energy consumption. Conducting a load study involves measuring the current and voltage on each phase of the transformer over a period of time. This data can be used to calculate the power and energy consumption on each phase and to determine the load balance and power factor. A load study can be performed using portable power quality analyzers, which are devices that can record voltage, current, power, energy, power factor, and other electrical parameters. The data collected from the load study can be used to create a detailed model of the load connected to the transformer. This model can then be used to simulate the impact of current transformer loss on energy measurement. Consulting with the utility provider is essential because they have detailed knowledge of their metering infrastructure and billing practices. They can provide information about the specific type of meter installed, the metering configuration, and the methodology used to calculate energy consumption and demand charges. They can also provide historical data on load profiles that can be used to assess the impact of current transformer loss. The utility provider may have established procedures for handling current transformer failures and recovering lost revenue. These procedures may involve using statistical methods to estimate the missing energy consumption or negotiating a settlement based on historical data and load profiles. If the utility provider's proposed settlement is not acceptable, you may need to negotiate with them to reach a fair and reasonable agreement. This may involve presenting your own analysis of the impact of current transformer loss and proposing an alternative settlement based on your findings. In some cases, it may be necessary to involve a third-party mediator or arbitrator to help resolve the dispute. Consulting with an independent expert or engineering firm can provide an unbiased assessment of the impact of current transformer loss. These experts have the technical knowledge and experience to analyze metering data, conduct load studies, and develop accurate models of energy consumption. They can also provide expert testimony in legal proceedings if necessary. When selecting an expert or engineering firm, it is important to choose one that has experience with metering systems, power quality analysis, and revenue recovery. You should also check their credentials and references to ensure that they are qualified to provide the services you need. The expert or engineering firm can perform a comprehensive assessment of the impact of current transformer loss, taking into account all relevant factors such as metering configuration, load type, historical data, and utility billing practices. They can then provide a written report summarizing their findings and recommendations. This report can be used to support your negotiations with the utility provider and to develop a fair and reasonable settlement. Negotiating a settlement with the utility provider involves reaching an agreement on the amount of revenue to be recovered. This agreement should be based on a clear and accurate understanding of the impact of current transformer loss and should take into account all relevant factors. When negotiating a settlement, it is important to be prepared to present your case clearly and persuasively. You should have all the necessary data and documentation to support your claims and be able to explain your reasoning in a logical and concise manner. You should also be willing to compromise and to consider the utility provider's perspective. The goal is to reach a settlement that is fair to both parties and that avoids the need for costly and time-consuming legal proceedings. In summary, recovering revenue after a current transformer loss is a complex process that requires careful analysis and negotiation. By understanding the factors that affect energy measurement, consulting with experts, and gathering relevant data, you can reach a settlement with the utility provider that is as close to actual usage as possible. Consider these additional factors. The age and condition of the current transformers can also affect their accuracy. Current transformers can degrade over time due to factors such as heat, moisture, and vibration. This degradation can cause them to become less accurate, which can affect the energy measurement. Regularly inspecting and testing current transformers can help identify potential problems before they lead to significant errors. The location of the current transformers can also affect their accuracy. Current transformers should be located in a clean, dry environment that is free from excessive heat and vibration. They should also be properly grounded to prevent electrical noise from interfering with their operation. The burden on the current transformers should be properly matched to the meter. The burden is the impedance of the meter and the wiring connected to the current transformers. If the burden is too high, it can cause the current transformers to saturate, which can lead to inaccurate measurements. The utilities metering policies and procedures should be reviewed to ensure that they are consistent with industry best practices. The policies should address issues such as current transformer testing, calibration, and replacement. They should also specify the procedures for handling current transformer failures and recovering lost revenue. In some cases, it may be necessary to upgrade the metering system to improve its accuracy and reliability. This may involve replacing old current transformers with new ones, installing a more accurate meter, or implementing a more sophisticated metering configuration. The cost of upgrading the metering system should be weighed against the potential benefits of improved accuracy and reduced revenue losses. Continuous monitoring of the metering system can help identify potential problems early on. This can be done using a supervisory control and data acquisition, also known as SCADA system or other type of monitoring system. The monitoring system can track parameters such as voltage, current, power, and energy consumption. It can also generate alarms if any of these parameters fall outside of acceptable limits. Regular training for personnel involved in metering operations can help improve their knowledge and skills. The training should cover topics such as current transformer theory, metering configurations, data analysis, and troubleshooting. It should also emphasize the importance of accuracy and reliability in metering operations. Documentation of all metering system components, including current transformers, meters, and wiring, should be maintained. This documentation should include information such as manufacturer, model number, serial number, and date of installation. It should also include records of all testing, calibration, and maintenance activities. The documentation can be used to troubleshoot problems and to ensure that the metering system is operating properly. Regular audits of the metering system can help identify potential weaknesses and areas for improvement. The audit should be conducted by qualified personnel who are familiar with metering systems and industry best practices. The audit should cover all aspects of the metering system, including current transformers, meters, wiring, data collection, and data analysis. The findings of the audit should be used to develop a plan for improving the metering system. Consideration of the potential for fraud and theft should be kept in mind when designing and operating a metering system. Measures should be taken to prevent unauthorized access to the metering system and to detect any attempts to tamper with the equipment. Data from the metering system should be carefully reviewed to identify any suspicious patterns or anomalies. In some cases, it may be necessary to install security cameras or other surveillance equipment to deter fraud and theft. Compliance with applicable regulations and standards should be followed when designing, operating, and maintaining a metering system. These regulations and standards may cover topics such as current transformer accuracy, metering configurations, data collection, and data reporting. Failure to comply with these regulations and standards can result in penalties and fines. Remember The specifics of the situation, such as the exact configuration of the metering system, the characteristics of the load, and the policies of the utility, will dictate the best approach to revenue recovery.